Hello, this is Jack Jackson. Today we're going to be talking a little bit about series convergence test. We have seen that infinite series, which are based on adding up infinitely many terms from an underlying sequence of constants, may converge to a finite sum, or it may not. Um, let's make that singular. Series, the word is both singular and plural, by the way. Determining this is a goal of this section of the unit. Here we will develop a series of tests that can be applied to series to determine if they converge or not. We'll learn characteristics of certain types of series, and from them we will determine which test is likely to produce a conclusion. Ultimately, we will learn how to apply and when to apply the divergence test, integral test, comparison test, limit comparison test, alternating series, ratio, and root tests. These are all the different series convergence tests that we will look at. Unfortunately, we will usually not be able to determine what the sum of a finite convergence series is, even when we are to determine that it does in fact converge to a finite sum. Typically, we will only be able to determine that the infinite series converges or diverges. Sometimes we will be able to determine some bounds on the sum so that we know that it is above or below some number, but we won't usually be able to find the exact value of the sum. The sum of a geometric series is an exception. We were not only able to find exactly when an infinite series, geometric series converges, but we're also able to compute the exact value of the series when it does converge. That's pretty rare. So this section on convergence tests forms a major part of the unit. However, it's not really the main goal, but rather a means to a further end. Although these convergence tests are interesting and worth studying in their own right, the main reason that we are studying them is to apply them to determine the endpoints of radii convergence for power series. Power series, which we will get to later in the unit, is the most important topic for the unit. However, before we get there, we need to master these series convergence tests. So let's look at the first one. The first one of these is called the divergence test. Now, the divergence test is just that. It tests to see if a series diverges, but it does not tell us when a series converges. So the divergence test says if the limit of the underlying sequence, the limit as k goes to infinity of a sub k is not 0 from some sequence of terms a sub k, then the series, the sum from k equals 1 to infinity of a sub k, has to diverge. So the divergence test basically will tell us when certain series diverge. So suppose that we have a sequence a sub k which does not have a limit of L equals 0. Does not have a limit of L equals 0. So it could have a limit that's not 0, or it might not have a limit. So by the definition of the limit of a sequence, there is some positive number epsilon, so that no matter how far to the right we go, there are still infinitely many terms of AK more than epsilon away from 0. If these terms are all above 0, then the limit definitely is diverging to infinity, because we're adding more than epsilon infinitely many times. If these terms are all below 0, then the limit diverges to negative infinity, because we're adding uh, again, adding epsilon, which is negative, we're adding minus epsilon uh, or more infinitely many times. If some of these terms are above and some are below 0, then the sequence of partial sums will be bouncing up and down, but it will not settle down to a limit. In any case, if the underlying sequence does not have a limit of 0, the infinite series diverges. So the divergence test establishes a basic minimum condition that a series must have in order to converge. It indicates that the only way a series has any hope of converging is if the underlying sequence of terms converges to 0. If we can simply show that the underlying sequence converges to a limit other than 0, or it doesn't even have a limit, then the corresponding infinite series must diverge. On the other hand, if the limit of the underlying sequence is 0, that's not enough to determine that the series converges. It might still converge, but it might diverge. This makes the divergence test the easiest to apply, but it's often inconclusive. So we can use the divergence test to show that the following series converge. See if you can sort of work out the details for these sequences: 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, and so forth. Or the sum from k equals 1 to infinity of sine of k. Or the sum from k equals 1 to infinity of k squared plus 2 over 3k squared minus 5. Or the sum from k equals 1 to infinity of e to the k over 3k to the square minus 5. The limit of partial terms does not exist on the first one, so the series diverges by the divergence test. The sequence of partial sums is 1, 0, 1, 0, 1, 0, 1, 0, which does not have a limit. On B, that was for A. For B, the limit of terms does not exist because sine of k takes on infinitely many values within the interval -1 to 1. It doesn't necessarily, may not take on all of those values because k is only a natural number, but still it's going to have kind of all the way up and down that range of values bouncing back and forth. So the series diverges by the divergence test. It doesn't have a limit. And the next one, the limit of the terms does exist. It's 1/3. And since this limit is not 0, the series diverges by the divergence test. And this one here, the top and bottom both go to infinity, but the top's going faster. The limit of the terms is infinity, meaning it doesn't exist. So clearly the series diverges by the divergence test. So we'll go on to the integral test next time. The divergence test was our simplest test, but it doesn't always work because a lot of the problems you're going to have in homeworks will have a limit of the terms being 0.